so like a bit of standard fabrication techniques for samples. And so you would start, so this is an example with a little animation. So you would start from a substrate. So all these circuits are fabricated, so they are superconducting circuits, but they lie on a substrate, right? And the substrate actually plays often a role in the sense that its non-idealities play a role. Often people would take silicon. So here this is silicon oxide, but this is a bit old slide. Now everyone would use silicon. And then you use a layer of resist to fabricate the junction circuits. And then you would start by writing some circuit with an electron beam pattern. So the electron beam breaks links. The resist is a polymer, right? So the electron beam will break some links in the polymer, changing its solubility with respect to some solvents, so that you can then develop it. And developing it will just make holes in the places that have been irradiated with electron beam, right? This is principle of modern fabrication techniques in semiconductor industry as well. And so then you are left with a resist mask. So one specificity is that this resist mask is suspended in the sense that there is a bit of space below. And the reason is that we want to fabricate the junctions. This is how we fabricate the junctions. And the idea is that then what you do is you evaporate some metal with an angle with respect to the normal incidence. And so you will have some image of this mask that will be a metallic, the metallic thin film will be deposited on the substrate, but with a certain displacement with respect to the initial mask. And this is the result if I would remove the resist mask, but the resist mask is still here. Then you would oxidize this first layer. So the whole first layer of aluminum would be then oxidized, and we would have a very thin layer of aluminum oxide. This is going to be the tunnel junction. And then what you do is to evaporate a second layer of aluminum with another angle. And the result is that now if you remove the resist, you see that you have these two layers overlapping, and now you see that you have a region where you have some overlap between the two layers, and where the current is obliged, if you want to go through this loop, for instance, the current is obliged to cross the boundary between the two layers. These are the Josephson junctions. Right? And you see that you have also, in this process, you have other junctions that are bigger, but that are in general neglected, but sometimes they also play a role. Right? But this is the principle. So this principle is called shadow evaporation. And the reason you have to do this is that you don't want, this is done under vacuum, this evaporation is done under vacuum, and you don't want to take your sample out to change and to redo an evaporation, because the oxide layer needed for the junction would not be clean enough and would be actually too thick even. Right, so this is, then you get images like that. So when you will look through the literature, you will maybe see images of samples, and you will see images like that. This is a very old circuit, and this is from the quantronium experiment, that's from 2002, but the fabrication techniques have, for the essential, not changed. This is still, shadow evaporation is still the way that the best junctions are done. So this has not changed. And so here you would see this circuit, and you see that you have, the circuit itself is this loop, these are the two junctions, this is the island, and then you see these weird images, right? And this is totally useless. Indeed, these are the shadows of the first evaporation, and they are useless, but they need to be there just to fabricate, to have this junction. This is why you will see, if you look at images, you will sometimes see, oh, I have the impression that there is a ghost image, right? This is due to this shadow evaporation technique. And the junctions themselves, they are like, 150 by 150 nanometers typically. Right, so this is another example. This is a circuit that I fabricated during my postdoc long time ago. And this is more recent pictures we took from a device we did in the group in Saclay. And this is even a suspended transmon qubit, where you see the junction is here and it's actually suspended. We have removed the substrate below to even minimize the electric losses. So the junction, the Josephson junction is like this, is really standing over the vacuum. All right, so this was just the end, in a sense, of the first lecture. And so today I want to discuss the readout of superconducting qubits. This is something that I did not explain yesterday, even though I showed some data, right? I didn't say exactly what was measured. And an important part of this lecture is that the readout of superconducting qubits is done via a microwave resonator. This is really the take-home message that you should bring. And I will then explain how. So I will first explain how the coupling to a microwave resonator works, what is the physics of it, and then how the qubit readout works in theory and also in practice. So I will give a little bit of experimental details in this lecture, because it is not only interesting, I think, for experimentalists, it's also good from a conceptual level. There are some interesting things that are both experimental and theoretical at the same time, and conceptual. All right, so maybe to start with, just to remind you of the kind of the goal of ideal qubit readout, right? So the situation is the following: you have your qubit, which is in a coherent superposition, let's say arbitrary states, alpha 0 plus beta 1, and you want your readout to be able to be switched on. And then the best thing that a readout could tell you is that it could give you 1 with a probability module beta squared. And if it does give you 1, then normally if you apply standard von Neumann postulates, etc., then the qubit state after that should be 1. Right? Which means that if you keep measuring it, you should find 1, 1, 1 exactly. Right? So this is a bit the best readout you could imagine. This is called, it should be high fidelity, meaning that the results of the readout should follow the initial probabilities that are encoded in the initial quantum state. And then ideally it should also be quantum non-demolition, which, in a very maybe operational definition of quantum non-demolition, it would be that you can repeat it, right, many times and find the same result. And then at some point, you will have some relaxation, because the qubit has a finite T1 and it will eventually relax back from 1 to 0. But how to do this? So this is clearly, in a sense, the goal of the best readout. But how to do this was, in fact, a difficult and interesting question for superconducting qubits that has brought a lot of conceptual innovations, because the research on qubits has started in 1999. But I would say this question was really fully solved maybe only 5 to 10 years ago. So it took really 10 to 15 years. So it was much more difficult than anticipated. And it brought a lot of new features. So, the problem is that, this, first of all, it's not so easy, because this readout should be fast if you want it to be high fidelity, fast compared to T1. But T1 in superconducting qubits is relatively short, even though it has improved in the recent years. This is still, a few tens of microseconds for the best cases. So it means that, and of course the fidelity is, you want the readout as fast as possible, because your fidelity will be limited by the ratio of the measurement time over T1. So if you want high fidelity, it should be many, many orders of magnitude below T1. So it means you need a fast readout. It should be fully non-invasive, right? Which implies that the readout process itself should not induce transitions. This is quite obvious. And the readout should be completely off during the quantum state manipulations. And really all these requirements are, it took time, but they are fully satisfied by the coupling to a microwave resonator, which is used for readout, as I will explain. All right, so which means that, yes?
Is there a lowest limit for the readout time?
I would not know how to answer this question. I would say that clearly the shortest time you could imagine. I mean, if you know, I would say the fundamental limitation would be the Larmor frequency of the qubit, right? Because anything faster would be non-adiabatic, and then you would induce transitions. Now, in practice, it's, I mean, the gap between the actual measurement times and this time are very big. So it means maybe we have a lot to gain, but yes, maybe there are some other things that I don't have in mind. I don't know. That's a good point, yes. But I would say, yes, that's, you know, then it would be, of course, sub-nanoseconds. That would be like a few tens of picoseconds. Right, so the you know, so in in optics, resonators would be, you know, in optics, electromagnetic fields live in 3D, right? So in general, so you always have to take care about transverse modes, etc. Except when you have guided, so nanofibers, as Derek explained, then or fibers in general, when you have a waveguide, then you have a 1D propagation for light. All circuit QED, all microwave, the microwave that we use in this superconducting qubit physics story is guided. So it's actually very convenient because it means that we have only one-dimensional propagation. So microwave can only be absorbed, be transmitted, or reflected. That's it. Right? So it's really makes things so much easier, and this is, I think, one of the powers of this field. So okay, so you see the resonators that we're gonna consider are in general so microwave Fabry-Perot resonators. So it's just a coaxial cable. Again, we use guided microwave modes, and you just interrupt them, right, to coupling capacitors that will act as weakly transmitting mirrors, and then you will have the Fabry-Perot physics with you know, the microwave bouncing back and forth and creating a resonance whenever the wavelength is satisfies this relation with respect to the length of the waveguide, right? And so so how is this implemented on chip? Because remember that we have these junction resonators, so we want to couple these junction qubits to these modes, right? And so one of the most popular way to do this is via this geometry. So this geometry, you see that here I have this substrate, which is again just a table. Think of it just as a table. And then it is covered with superconducting thin film. As I explained, it's evaporated. And then we have just drawn by lithography again some waveguides. So you see that there is a ground plane on both sides, and then in the middle there is a central conductor. This looks like a coaxial cable taken, you take a slide, I mean like a slab of coaxial cable, right? But even though it's only 2D, it still works to guide the line, the microwave, right? Because these dimensions are much smaller than lambda. So this is really like in the lumped element limit. This is in the near field. This is absolutely a near field. Huh? This is like many orders of magnitude smaller than lambda. And so this is a guided mode. And microwave just can propagate very well, especially with a superconductor, because there are no ohmic losses, as I already explained. Right? And then if you interrupt this transmission line in two places, then here you have this capacitive coupling on both sides, and so this implements this Fabry-Perot resonator. Okay? So just a little bit of vocabulary. So you see, if I look at the transverse, you know, it's possible to compute the fields, but this is even just a schematic representation because you can really understand very easily how this works. So the ground plane would be at 0 potential, and then the central conductor potential would oscillate, and this would generate an electric field that is like that, right, in space. And then you will also have currents flowing both through the central conductor and through the ground, and they generate a magnetic field which is in this form, right? This is the transverse pattern, and then the mode propagates. All right. This is called, this guided modes, they are called coplanar waveguides. And there is a whole family of modes. You can have, slot lines modes, microstrips, etc. So this is the, in a sense, the planar modes for microwaves. Right. And it's a TEM mode. All right. So this is just an example of a resonator, characterization in our group at 10 milli-K. This is an aluminum resonator, and you can measure the reflection coefficient and the phase, and it resonates at 7.2457 gigahertz. And from that, you can extract the quality factor of the mode, and you can extract, and in fact, these modes, they have two, so if I look at such a resonator, but in reflection. So imagine I just have one port here. I'm just measuring the reflection coefficients. Then there are two parameters that are relevant. One is the coupling. So the total quality factor is the result of two loss channels that should be distinguished. One is just the coupling of the resonator to the external line, right? Because evidently, this also limits the time that the energy can be stored in the resonator, because it also leaks via the input line, right? So this is what we call the external quality factor, or the coupling quality factor. And in a sense, this is engineered by just doing the lithography and computing and doing simulations, right? So you can have any value you want, right? But then it's not the only story, because we use superconductors, but as I mentioned, they are not entirely lossless. There are still some loss mechanisms remaining, even though, thanks to superconductivity, the quality factors can be quite high. And so there are still internal losses. So, we can plot the total quality factor, which is the sum of the internal quality factor and the coupling quality factor. But we can also, from these fits, we can measure the internal quality factor. And this is just an example of measurement. This is completely routine in our labs and in many labs. And so we can measure this quality factor as a function of the mean intra-resonator photon number, right? And if things were simple, this would be a constant, because the coupling quality factor certainly is this is linear electromagnetism, so this should not depend on power, and the losses should also not depend on power. Except they do. When you measure the losses, there is a weak dependence. Sometimes it's much stronger than that, but I just took, kind of simple data. And we see that this is a general feature of these resonators, that we observe power-dependent internal losses. And these power-dependent internal losses are now very well understood, and they are a signature that these internal losses are caused by a bath of two-level systems. So this is of microscopic origin. This is a bath, and so interestingly, no one knows what physically are these two-level systems, but we have many evidence that these are real two-level systems. They are anharmonic, so it's really to be taken to the exact sense of this. And they are quantum mechanical, they can be coherently measured, etc. There is a whole, the literature on two-level systems is maybe one of the big success of superconducting circuits, is that they provide an enormous way, an enormous progress in the way that we can probe these two-level systems and see them and measure them. It's really quite spectacular. But I won't speak about that. But behind this word, there is like thousands of articles. So now coming back to the real story, as I said, we want to interface qubits with resonators. And so this picture is borrowed from Rob Schulkopf, from this paper of Rob Schulkopf and Alexandre Blais and Steve Gervin at Yale in 2004. And this is a very successful picture, because this was a very successful idea. And they were really the first to, so we did related things at the same time, but they were really the first to imagine how to interface a superconducting qubit with this coplanar waveguide resonator, and this was a very successful idea. In fact, then so you see that here the idea is, okay, let's take the superconducting qubit. This is again a Cooper pair box. Maybe you don't see it, but this is the island, and now it's connected to the ground plane via two Josephson junctions. So you recognize the Cooper pair box as I drew it yesterday morning, right? So we have this Cooper pair box, and now instead of having a gate voltage, it's connected capacitively to the microwave mode of one coplanar waveguide resonator at a place where the electric field is maximum, because we want to couple them electrically, right? This is the whole idea. And so, and this whole idea was so successful that it gave rise to, in a sense, an entire field, which is called circuit quantum electrodynamics. And in a sense, nowadays, circuit quantum electrodynamics is synonymous with superconducting qubits. The two fields are now entirely merged, because qubits now go together with cavities, but it was not the case at the time. And so why is it called circuit quantum electrodynamics? This is by analogy with cavity quantum electrodynamics, because this is really and deeply the exact same physics, as I will try to show you. And so in particular, it's absolutely the same. So I would say maybe absolutely all results that have been obtained with Rydberg atoms coupled to superconducting cavities have been obtained now in superconducting circuits, and vice versa. Right? The two fields are kind of merged. These are just tools to study the exact same physics. Right? And so, of course, there are references. You probably know. So this is just to show you that there have also been some more recent developments that, in fact, these superconducting circuits, as I told you, okay, it's nice if the resonator is directly on the chip, right? It makes sense to have them closely interacting, capacitively coupled. But so again, at Yale, Rob Schulkopf realized that you don't need to do that. Maybe you can also, the circuits are so big that they can also couple directly to a 3D box, right? Just you know that a microwave resonator is the simplest thing you can do. It's just a metallic, it's just a hole in a metallic box, right? And so, so this is one of these boxes. In fact, you have two boxes. You see that you have two cavities. Here, there is, you don't see it, but there is a cover that will just close so that these holes will be entirely really surrounded by metal. And this metal is superconducting, so you have a high Q resonator. And so you see that here I have a transmon qubit, and it's actually coupled to two cavities. And just because it stands in these modes of two cavities, and the couplings are, they can be tuned more or less at will. So yes, let's see a bit more in detail how this works. And so, so again, let's come back now to equations, and this will be fast, don't worry. So we have our Cooper pair box, you recognize it, with the junction and the capacitor, and this is the island. And it's coupled by a gate capacitor, again to a gate voltage. But in addition, now you see that I have this piece of coaxial cable, and that's my resonator, right? So in a sense, the only difference with what I said yesterday is that the gate voltage, instead of having this DC gate voltage, there are also the quantum fluctuations of the voltage of the resonator itself, right? And the voltage operator of the resonator is simply A plus A dagger times the quantum fluctuations of the voltage at the resonator at this point. So that, and then we can just plug this into the total Hamiltonian. That will be the sum of this Hamiltonian plus the resonator Hamiltonian. And now in the gate voltage, I have this DC gate that, you know, anyway will vanish because we are in the transmon limit and the DC gate doesn't matter. But then we have this coupling term because NG includes these quantum fluctuations of the voltage in the resonator, so that I have a linear coupling between the voltage operator and the charge, you know, the charge operator of the Cooper pair box. And you see that I have this coupling term here that couples, again, A plus A dagger to N operator. And it's actually very easy to now take this Hamiltonian. Now you see that it looks quite complicated, but okay, first thing we do, of course, is we project it on the two lowest states of the qubit, and we perform this two-level approximation, and you know, then you're left with only Pauli operators, so things suddenly become a little more, you know, physicist friendly. And then you also do the rotating wave approximation, and then we obtained very straightforwardly this Hamiltonian. This Hamiltonian I didn't mention. This is the, of course, the resonator Hamiltonian. I hope you're all familiar with this. It's just the resonator frequency times A dagger A, number of excitations. So you see that the total Hamiltonian is the qubit Hamiltonian, qubit-free Hamiltonian, plus the resonator-free Hamiltonian, plus just a linear coupling between the dipole of the Cooper pair box and the dipole of the resonator. So, and the strength of this coupling is expressed by this parameter G, which is the coupling constant between the qubit and the resonator. And this is the celebrated James Cummings Hamiltonian, and we are going to see a little bit more in detail how it works. Now, let me go back just a little bit quickly to this value of G. And you see that to just insist on the power of electrical circuits. So here G is the product of some voltage fluctuation, delta V naught, which are the resonator fluctuations, then times some factors. And you see these factors are actually gate capacitors. Gate capacitor, I can design it as well with my lithography. I can make it small, I can make it big. Really, there is a lot of flexibility because this is really a kind of macroscopic parameter that is chosen by design, right? This is a little less easy to design because, you know, it's part of the whole physics of the qubit, but this coupling term, you can really make more or less as big as you want. And so this geometrical dependence of G makes it very easy to tune by design the circuits. And remember that the transmont qubits that I showed you yesterday, they are like 100 microns large, right? So you imagine that this coupling constant can be made very big compared to the coupling constant of an atom to the field in a cavity, right? This is the power of circuits. And yeah, so G can be brought as high as 200 megahertz or even higher in some cases, right? So G is never too small. I mean, in fact, it's more difficult to reach the weak coupling regime in superconducting circuits. They are naturally strongly coupled together, right? This is what, yes, I say here. And remember that the decay rates of these circuits are in the 100 kilohertz range, right? So there is a big range of the G is like several orders of magnitude larger, can be several orders of magnitude larger than the decay rate of the circuits. And so, so let's see now a bit more, because I don't think this has been seen already in the school, but maybe I will go a bit fast because this is quite simple. But okay, so we have this James Cummings Hamiltonian, and you know that you may know that one of the nice features of this model is that it's actually exactly solvable. It's very easy to solve, and the reason is that this term couples only level doublets, right? These are the uncoupled states of the joint system, both the qubit and the resonator. 0, 1, 2, 3 describes the Fock states of the resonator. And for the qubit, I have considered only the two-level approximation, meaning that I forget that it's a multi-level system, that it has higher excited states, right? But yes, this is a good approximation for many things. And so, in fact, this term, so G0 is still an eigenstate of the system. However, in the higher excitation manifolds, these levels become coupled, and what is coupled is Gn plus 1 to En. And that's it. They are not coupled all together. So it's really just 2 by 2 matrices block diagonal. So this is possible to diagonalize even for an experimentalist. And this is the result. And the interesting thing is that because of this coupling, the coupling constant is actually scales like the square root of the number of photons, right? And we can introduce the detuning between the two systems, right? So because the cavity and the qubit do not need to be on resonance. There will be not too far from resonance, right? Because you want them to interact, but they can be detuned, and the detuning is an important parameter, right? So the parameters of this physics, there are two. It's the coupling constant and the detuning. Okay. And then you can just compute the eigenstates, and the eigenstates are evidently coherent superpositions of the two states En plus Gn plus 1 with a certain mixing angle that can be computed very easily. Right? And so this is how it looks these are the uncoupled states, En, Gn plus 1, as a function of the detuning. So they cross at 0, right? And then when we would branch the coupling, these are the energy eigenstates, and you see that there is a splitting 2g square root of n plus 1 between the eigenstates minus n and plus n. And in particular, even when we consider the states E0 and G1, there is also a vacuum Rabi splitting that is equal to 2G. Right? And this is a little bit the hallmark of observing this avoided level crossing is the hallmark of the strong coupling regime, because these are only the eigenstates, but if we were in a regime where the damping rates were much larger than the coupling rates, you would not see this, because then the levels become very broad, and then you do not see this spectroscopy, right? And so here there are two interesting limits. One is the resonant regime, where the two systems exchange energy, right? But there is also the dispersive regime, where the detuning is much larger than G. This sounds a little bit weird to go into this regime, but it's actually very powerful. And so in a sense, the resonant regime is very good when you want to engineer non-classical states of the electromagnetic field itself, because the qubit is a two-level system, and so it's a very efficient source of single photons. For instance, if you want to build arbitrary states of the microwave field inside the resonator, it is possible by using the qubit, and then playing with the resonant interaction of the two systems. But the nice thing in the dispersive regime is that you see, because the detuning is much larger than the coupling constant, the two systems are not going to exchange energy anymore, and that's good for qubit readout, evidently. If you want to read out the qubit, you don't want to perturb its state. You want to keep its state unchanged. And then you should avoid any exchange of energy. However, in this dispersive regime, there is still a remaining effect of the cavity, and that's a dispersive effect. So there are small frequency shifts that are measurable, right? As we will see. So just to show you a little bit, so this is the only slide about the resonant regime to a little bit of history of superconducting qubits. So this was the first observation of the vacuum Rabi splitting with superconducting qubits. Of course, this vacuum Rabi splitting was observed before with atomic systems in atomic cavity QED and quantum dot systems, of course, in Jeff Kimball's group, Harosh group, and others. But so with circuits, this was the first data obtained by Andreas Wallraff in 2004 in the Rob Shulkoff group. And you see that here this is the resonator transmission when the qubit is off resonance. So you just see this Lorentzian peak. And when the qubit is brought in resonance, you see these two peaks that are very well separated. And they have this signature of the strong coupling, right? But you see that the ratio of coupling to line widths is like is quite good, but it's just a few. It's of order unity, but more modern data look like this. You see that now you see that you have really a big range between the coupling, and this is the coupling is this, and the line width, which is like more than 100 times narrower. And this is just from 10 years ago. All right, so now coming back, this is to show you that experimentally these circuits are deep in the strong coupling regime. And so the James Cummings physics is very valid. And so now in the dispersive regime, coming back to the dispersive regime, there is a simplest form of the Hamiltonian that, you know, the James Cummings Hamiltonian can be approximated by another Hamiltonian, which is the following. And you see that we have, again, some sigma z term. So this is, again, the qubit term. But now the resonator term is also here, omega c a dagger a. But then the coupling to resonator interaction, instead of having this sigma plus a plus sigma minus a dagger, it's transformed into an interaction which is sigma z a dagger a. So sigma z does not induce any energy transition between state 0 and 1, right? So if you apply sigma z to 1, it stays in 1. And a dagger a also preserves the photon number because it's the photon number operator, right? So you see that this Hamiltonian, in this Hamiltonian, the energy eigenstates, like the Gn or En, they are still energy eigenstates of this dispersive Hamiltonian. Remember that this is the dispersive regime, right? So we are in the dispersive regime, implying that it's only valid when the detuning is much larger than the coupling. So the two systems do not exchange energy. But now instead of having G, we have another rescaled coupling, which is the dispersive coupling constant, and which is G squared over delta. This should remind you some second order perturbation theory, because this is what it is, right? So we have a frequency shift, and now you see that what is the effect of this term? Well, if I look at the way this Hamiltonian writes, so it's just take it as what it is. A dagger A is the resonator Hamiltonian. What's in front is its frequency, so it just means that now its frequency is dependent on the qubit state. Right? So it's as simple as that. And this is the dispersive regime. So the cavity can probe the qubit state non-destructively. So by just probing the cavity frequency, we will have some information about the qubit state. Now, you can also rewrite this Hamiltonian in a way that will show that, conversely, if you put some photons inside the cavity, there will be a shift of the qubit frequency that is proportional to n. This is unavoidable, right? I mean, the two systems are coupled, so if you have one, I mean, there is always a back action, right? This is the back action of the dispersive readout. When you put photons in the resonator, you will shift the qubit frequency. And if the photon number is noisy, this will introduce some dephasing. And in particular, where would the photon number noise come from? Well, you know, if you want to measure the resonator with a coherent state has fluctuations of the photon number. This is called the shot noise. This is an intrinsic quantum effect, right? And the shot noise will cause dephasing of the qubit. Well, that's a good thing because, you know, if we want to measure the qubit, we also have to dephase it. So the two things go together. All right. So having said that, this is a bit the theory of how the dispersive readout will work. And now I would like to go a little more in detail into practical things about this readout, and because they are also conceptual, as I said. So what I want to first say is something that I have not insisted on so far, is to speak about temperatures. Because, you know, so far I told you, oh yes, we just have, so the only mention of temperature that I have done so far was to say, okay, if we want to be in the quantum regime, the temperature should be lower than h bar omega over k. Okay, but which temperature? So, you know, there are many temperatures in this story, and this is what I want to have you realize. When you cool a sample in a cryostat, the sample is connected by some, you know, copper, some good material with good thermal conductivity to the coldest place of the fridge, which will be the mixing chamber. And this means that the substrate itself will be cooled to the fridge temperature. So this is the phonon temperature. But this is not the interesting temperature for us. For us, the interesting temperature is the temperature of the microwave field inside the microwave photons that live in this chip, that are trapped in this chip. Because also the qubit itself is microwave excitations. And as we will see in a minute, and as you can guess, the two temperatures are very strongly decoupled. Why are they decoupled? Because of superconductivity, right? Superconductivity means that the photons are not absorbed by the metal, by the substrate, so they are decoupled from the substrate. So you can have any difference in temperature between the substrate and the microwave field. So the message is, it's not enough to just cool down the sample. By far not enough. What you want to cool is the microwave field. There is yet another temperature, and that's the temperature of the electron condensate inside the superconductor. And this is yet another story, because you may have excitations inside this condensate, and the three temperatures are largely decoupled. Right. So now let's imagine that we want to, we have our substrate and chip. So this is an example. You see that here I have this coplanar waveguide resonator, and at the end I have a qubit. Well, it doesn't matter. It's true for any Josephson device, right? And imagine I want to measure it. So I cool it down at 10 milliK, and then I attach microwave cables, right? And then I measure. So is it enough? Is it enough? No. Why not? Well, you know, these cables are pretty lossless. And then, you know, at 300K, you have 300K noise. And at thermal equilibrium, you know, at 5 gigahertz, you have 10 to the 3 photons per mode. Right. So now if you do nothing, this mode, which is directly connected to these cables, will acquire a microwave field temperature of 300 Kelvin, even though the substrate is at 10 millikelvin. This is absolutely no problem. It's fine. Except it's not fine for measuring the qubit, because you know, it will, as I said, the qubit is a multi-level system, so you really want it to be in the ground state to high probability. So if you do that, you'll never see anything, right? Because of the thermal noise. So how to deal with the thermal noise? Well, there are two ways, and this is different from the input because you have an input line and an output line. So in the input line, it's quite straightforward. What you do is you put attenuation. Well, attenuation, you could say, okay, I'm going to attenuate at the entrance of the fridge. I'm going to put a big attenuator. Well, it's not quite very smart, because the attenuator itself is also at 300K, so it will radiate in the line. Anything that's at room temperature will radiate. Right? So if you place, so what is the key word here is that you want cold attenuation in the line. So okay, so this is, sorry, I forgot, this is 4 Kelvin. So the typical, you know, ideally you should put all the attenuation at 10 milliK, but this is not also very smart, because you're going to put some power in these lines. So then, you know, some of it should be, so there is a smart way to handle attenuation. It's good to put some of it at 4 Kelvin, because 4 Kelvin is already cold, so you will gain already from the thermal noise. You know, you will get 30 dB. But the 30 dB, so you will just get one photon after that. But the 30 dB itself is at 4 Kelvin, so it will radiate the 4 Kelvin radiation downstairs. Right? So you have to take care of that. This is how you design the cabling of a fridge. Right? So this is a typical good, it works well. You know, you can, then you can reach microwave temperatures of a few tens of millikelvin, 50 milliK or so. Note that nobody has ever reached a microwave temperature of 10 milliK. This is nearly impossible. Why is it so? Because the photon number decreases exponentially with the temperature. So in fact, the lowest temperature, if you want a certain temperature, you should attenuate maybe 100 dB or more to get to 10 milliK. Right? Okay, now, but now, can we do this on the output? Maybe we can do the same thing. Let's put 60 dB again. Is it a good idea? Maybe not, because we want to do a measurement, right? We want the signal to go out, and we don't have many photons, right? So if you put 60 dB, you have no signal, so you're screwed. So there is a key, the answer on what makes all these experiments possible is a microwave component called a circulator. And this is a key to all circuit QED experiments. And circulator works this way. So you have it's a 3-port non-reciprocal device. So you have some input that is routed here. And then what's reflected, or what comes from this port, is routed here. And, and what would come here would be routed here. So it's a lossless device, but non-reciprocal. So how is it useful in circuit QED? In this way. So what you do, and this is like really the standard circuit QED setup, right? This is how you would do. So this is our input line. Then we will have, a circulator is used to make reflection measurements, right? Because then you have this input signal, it's routed here, and then the reflected signal, which contains the information you want, is routed on the output line. So it's separated from the input, which is a good thing. But then, here on the output line, I have this thing. And so you see, so first thing is I have an amplifier at 4 Kelvin. So it's better to have it because, there are good amplifiers at 4 Kelvin. You get less noise. So it's a good thing. So I will come back to this point in a few minutes. But so we have our amplifier at 4 Kelvin. But you see that between the amplifier and the chip itself, I have another circulator. So why is it 4? Well, the amplifier itself sends noise. It sends noise, so it sends less noise than the 300K, but you can imagine that this is a noisy, you have noise coming from here. Now, what does this circulator will do is that it will take this noise, it will route it in this port, and now on this port, I can have a 50 ohm resistor, which is thermalized which thermally anchored at 10 millikelvin, so that it is cold itself. It will, because it's matched, it will absorb all the noise that comes back, but because it's at 10 millikelvin, it will not radiate any noise inside the device, right? So using the non-reciprocality of circulators, it is possible to have all the signal, you see that all the reflected signal is transmitted without any attenuation in the output, and still fully protect the sample against noise. Right? This is the key to circuit QED. All right, so just, there was also a shift in experimental techniques from wet fridges that, in a sense, use liquid helium as the coolant to much more user-friendly setups that are called dry fridges. And, in dry fridges, basically, you have no liquid helium. This is like a 30 centimeters diameter plate, typically. It's standing in a vacuum chamber, so you don't have any cold leak-tight connections to make. It's all at room temperature, so it's super convenient and easy. You have lots of space, so you can put lots of microwave stuff inside this fridge, and this is what people do. Right? And you can have tens of coaxial cables, or even hundreds in the very fancy, like superconducting qubit prototypes. These are the pictures that you see from Google or IBM. Right. All right, so now let's come back to the qubit readout itself. Let's see how it actually works. So we have the pulse. What we have is that we want to answer this question: is the sample is the qubit in state 0 or 1? And for that, we have a microwave source. Then we send a pulse at the cavity frequency. This pulse will enter the resonator. And then, depending on the qubit state, there will be a phase shift, right? So this coherent state will be shifted to alpha 0 or alpha 1, and then reflected. And this information on the qubit is now encoded in the phase, right? And so then the idea is, can we say if it's phi 1 or phi 0, right? So this is an example of this dispersive readout. These are very old data. I'm showing just for you to from our group, but it's very similar to what people do. So this is called two-tone spectroscopy, right? Because here you have two frequencies. You have the qubit frequency, which is detuned from the resonator, and you have the resonator frequency. And what you want to do is first excite the qubits at its resonant frequency, and then measure its state with the resonator and detect the phase of the reflected signal of the probe tone. And this is the phase of the probe tone as a function of the phase of the frequency of the drive frequency, and you see the qubit peak. Now this is, and you can do Rabi oscillations in this way, but these are very old data. You see that the Rabi time is actually very bad, but these are also old data because you see that here what I plot is just a phase, right? It's not like a probability of finding the qubit in the excited state. So why was it like that? Well, it's because, in fact, in these initial measurements, we were not able, and this has been the case for 10 years, in fact, it was not possible to discriminate between phi 1 or phi naught in one shot. So you would just have to average a lot, and then you would see some phase, right? But it was difficult to obtain enough signal to noise to discriminate between phi 1 and phi naught in one shot. And the reason for that is that this cryogenic amplifier is a real amplifier, and it has a noise temperature of 5 Kelvin, which is the lowest commercial, is the best that you can find commercially, but is not sufficient for discrimination in one shot. And so I just want to remind you maybe very quickly what is the noise temperature of an amplifier. This is like microwave engineering. And because there is a few interesting things to, it's conceptually, it's very simple, but it's conceptually, I think, powerful ideas that it's good to convey to you. So, you know, a real amplifier has a gain, right? But it also has, it adds noise. So imagine you have this ideal amplifier, and the idea is, imagine you have a source, like a 50 ohm resistor placed at 0 Kelvin. You will still see noise in the output, even though the input is fully noiseless. And the reason is that the amplifier itself adds noise. And so now this noise, N0, it is in general converted into some temperature in the following way. So you have this noise power, and now you replace this by an ideal noiseless amplifier connected to a source at a certain temperature, which is just this noise at the output referred to the gain, divided by the gain, right? Because the more gain, what counts is the signal is also amplified, so what counts is the noise referred to the input, right? Is the noise divided by the gain. So this is the right quantity, and this can be turned into some temperature, right? So in a sense, the noise temperature of an amplifier is the temperature that a fictitious load is the noise that a fictitious load at a certain temperature would create at the output of this ideal amplifier. Okay? And now there is a very interesting feature that I think we should all learn in like basic classes, but it's not the case in general. But I think it's something quite powerful. Imagine you have cascaded amplifiers, right? First one, second one, etc. You could say, okay, they should all be very good, right? It's not true. The only thing that counts is the first amplifier, and here is why. If you just do a very simple reasoning on these cascaded two amplifiers, you will see that this is equivalent to an amplifier with a gain G1, G2. This you will all agree, but with a noise temperature that is the sum of the noise temperature of the first amplifier plus the noise amplifier of the second amplifier divided by the gain of the first amplifier. Okay? So it means that, you know, the second amplifier could be, if this gain is 30 dB, you know, this noise temperature could be 1,000 times worse than the first one. It does not matter, right? So the noise of the first amplifier of the detection chain is what matters. And this is why, in this business, so our cryogenic best commercial amplifier is not good enough, so we need a first amplifier that's even better. And this amplifier is going to be at 10 millikelvin, and this is how people solve this problem of single-shot discrimination. And this was a motivation to build new generation of amplifiers that work at 10 millikelvin and that are basically working as well as allowed by quantum mechanics. Because it turns out that quantum mechanics tells you also some things about the best amplifiers that you can do. And so again, this is just this idea that an amplifier may add noise to a signal, you know. So even the signal is noisy, so of course, you know, the amplifier, even if it was ideal, would still be noisy. The output would still take the noise at the input and multiply it by the gain, right? This is obvious. But it adds more noise than that, right? And now, the best amplifier that quantum mechanics allows you to do was described by Caves in a very famous paper, and this is called Caves' theorem. And Caves' theorem is expressed here. This is Caves' theorem, graphically. Take this first picture. So here, this first picture describes, this is the input field, and this is you know, so this input field has a certain, you know, phase. This is the quadrature of the microwave field, so it has a certain amplitude and a certain phase. So the output signal would be of this amplifier would be multiplied by a certain gain, so you know it would go straight. And this amplifier, imagine this amplifier preserves the phase of the input signal. So then, you know, the amplified signal should be in a straight line compared to this. So this is the mean value. It also has fluctuations, and part of these fluctuations come from the amplified input fluctuations, right? This is this little magenta circle. But the total output noise is larger than that. And is larger than that by 1/2 extra photon noise. This is what Caves' theorem tells you. It's actually relatively easy to demonstrate. I don't have the time, but I can explain you if you are interested. And in a sense, this is not so surprising, because if we could amplify noiselessly both quadratures, it would mean that, in a sense, we would have a good quantum measurement of both quadratures at the same time. And that's not very possible, because these are two operators that do not commute, right? So this is part of Caves' theorem, but Caves' theorem also tells you that there is another class of amplifiers that does not preserve the phase. So you see that here I have my input signal with a certain phase, and this would be the output signal. You see the output signal, you know, if this quadrature of the input signal has been amplified, but this quadrature has been actually de-amplified. And now if I do this, I have an output which is like that. This is the mean value. And of course, it also has fluctuations, and these fluctuations are as stated by the gain. But that's it. There is no extra noise added by the amplifier. So it is possible. Quantum mechanics allows that. An amplifier that is phase, in a sense, phase sensitive, means that it will change the phase of the input signal, if you want, can be strictly noiseless. And this should not be surprising to you. This is really the analogous of homodyne detection in optics, right? In optics, you know that you can measure one quadrature absolutely noiselessly by mixing it with a local oscillator. This is the analogous of this feature. But this is, of course, phase sensitive and phase dependent. Right, so I have a few minutes left just to maybe describe you an actual, yes, I didn't give this name maybe. So these superconducting amplifiers that I referred to that enable this single shot readout of superconducting qubits, they are also built out of superconductors and Josephson junctions. So really this is the same technology as the qubits, and they are called Josephson parametric amplifiers. And this is now, again, a whole field of research to build the best Josephson parametric amplifiers. So this is a couple of slides from our group, but there are like thousands of references again. So the idea is, again, you take a resonator. This is the heart of the device. And this resonator, you make it a bit nonlinear and tunable by having squid. So we put an array of squids, but one is enough, right? So when you have this squid, this is the picture of the device, then you see that this resonator becomes tunable if you change remember that there is the Josephson inductance, so if you change the flux through one of these loops, this will change the critical current of the effective junction that is the squid, and then it will change the inductance, the Josephson inductance, which means that the total frequency of this circuit is going to be tunable. Right? And you can tune it over many, many line widths, but this is not the interest. So, okay, the nice thing is that here, first of all, you can tune the frequency of operation, right? You can apply some DC flux and then work at a certain frequency. But that's not, of course, the interest. The interest is to pump this frequency tunable resonator with a high frequency tone that will trigger parametric gain. And for that, you see that this is a resonator with a frequency omega naught. And so what we do is we pump this resonator with a flux that oscillates at a frequency twice omega naught, or around this value. Right? And when you do this, you have the phenomenon of parametric instability, of parametric amplification, which is a purely classical phenomenon, of course, but that leads to gain in the input signal. So you have now a weak probe. This is a strong pump tone that will, like modulate this resonator frequency, and then you have here this input and output ports that's in reflection, and the output signal is going to take some, pump photons and use it to gain power in the input signal. This is how it works. And so this is a typical gain curve. You see that you can have, so this is an old device, but you can have 20 dB gain over a bandwidth is quite narrow, at least in this first generation device was the case. And I don't prove it, but these amplifiers very generally are quantum limited. So there are experiments that prove it, but I don't show it here, but believe me, they actually reach this quantum limit. So this quantum limit here, you see that here, this is in the mode that is phase insensitive, phase preserving, so which means that the amplifier has to add half a photon of noise. Here I wrote, this is per quadrature, so it's quarter of a photon per quadrature, but in total it's half a photon. And, but it's also possible to operate this, this amplifier in this phase sensitive mode, where the gain is going to depend on the phase. And for that, obviously, the signal should have, oh, I don't know what, okay, sorry for that. But the signal frequency should be exactly half the pump frequency, right? And then the relative phase of the two signals will matter to see how much gain there will be. And you see this in this curve. When we change the relative phase of the two signals, you can go from a gain of more than 20 dB to an attenuation of more than 20 dB. Right? And this is exactly what we saw. And this is a mode in which, okay, if we have a signal that is on this quadrature, it will be noiselessly amplified. Right? And so just a few words to tell you that there are new generation parametric amplifiers. This is like the simplest, like single junction devices. They are called JPA or JPC or whatever. But there are new devices that are traveling wave parametric amplifiers that are more complex because they include like thousands of junctions, and in a sense, they are the propagating version of these devices that are based on resonators. These ones are not based on resonators, and they are much broader band, as you see. Here you can have near quantum limited gain over gigahertz bandwidth. All right, so let me now just give some single shot results very quickly because I'm a bit late. These are the first single shot traces that were obtained by Irfan Siddiqui in 2011. And you see that it's again this two-tone spectroscopy. This is the qubit and the readout tone. But you see that now we have traces in which we see directly the jump between, and you see it by eye, between the state 0 and state 1, right? There are like, seems to be two families of curves. Right? And these are the two states of the qubit. And this is now expressed by histogram. So you would integrate, what we would do is we would integrate this over a certain time and then repeat many times and plot the results on the form of histograms. And this is just taken from this paper to show without paramp, the two histograms are very similar in the ground and excited state, and now with the paramps, you resolve very well the two histograms, right? And you can even do continuous monitoring. When the T1s are very long, you can do some continuous monitoring of the qubit state and see weird things in the statistics, etc. All right, so this is all I wanted to say. Thank you for your attention.
Professor Roland this Hamiltonian dipole coupling.
Yes.
And I imagine this Hamiltonian dipole coupling can also be easily achieved on chip on with superconducting
Yes,
qubits.
absolutely.
I imagine just connect the qubits via straight lines, okay?
Yes.
And then, but in free space two atoms, and
Yes.
have to consider in non-trivial case, depends on their relative orientation spacing. There's an angle factor considered. So on chip,
Yes.
it's not straightforward. I think in imagine it.
Yeah, there are a number of experiments that have done that. So I mean, you have to realize that I'm just giving you a flavor of the field. Field of superconducting qubits is enormous. Pretty much any simple idea you can have has been done. This has been done. So so what people do, but there is a difference. Huh? That in the case, so as I said, this is one-dimensional microwave engineering. So then what people do, so you take this coaxial line, this coplanar mode that is without resonator. You can also just make a transmission line, right? And you can put 2 qubits inside this line. And you can look at subradiant states, superradiant states, and interaction mediated by microwave photons. It has all been done, yes, absolutely. Yes, I can give you the references if you're interested, yes.
My question is more that it's kind of hard to imagine how to introduce the angle factor.
No, there is, yes, so, okay. So here the dipolar interaction is mediated by so you see, it's a capacitive coupling, it's electrostatic. It's also, okay, dipolar interaction is also electrostatic. So maybe it's not the best answer. But you have a coupling, it's...
So there is, as they share the same mode, there is no
Yes.
still the
Yes.
dipole interaction, but they
Yes.
share the same mode. So the sigma plus sigma minus has in front of it a coefficient which is independent of the distance.
Yeah, sorry, maybe I could rephrase it. So, in fact, there is an angular dependence. And how would you show it? But it's just that, these are on-chip things, so you don't move them, you don't change their angle. But by thought, you could do that, right? You could take 2 qubits and then rotate them. Then the capacitive coupling between them would depend on the angle, You could have situation, if you make them perpendicular, you would have no coupling. So in fact, but the whole coupling is encoded into one. It's just that the dipole coupling is not really this simple formula, because we are not at all in the limit. This simple formula comes from the fact that the distance between the electrons is much, much, much bigger than the size of the atom. We are not in this limit. The atoms are very big. They are coupled, so you just do electromagnetic simulation. You extract one coupling, one capacitive coupling, and that's it. So this is, but in a sense, this is the same physics, except it's not in the small atom case, I would say.
About the amplification, if I understand, it's kind of using a squeeze state of the...
Yes, absolutely. So I did. It's not using it, producing. So you're right. I didn't say that. But if you just use this amplifier on the vacuum noise, acting on the vacuum noise, you will produce a vacuum squeezed state. Yes. Okay. Yes, absolutely. Yes, this has been used in many experiments. This has been.
Yeah, like the Vigo or the...
Yes, absolutely. Except now this is at microwave frequency, so it's not directly usable. But we have. So maybe I will say a few words tomorrow, then, if you are interested. Yes, because we've done an experiment where we use this squeezing to perform better measurements. Yes, better quantum sensing.